Hi everyone, this is the third video in our dynamic programming series, and today I will be talking about optimal binary search tree. So before that, just think about an example. Let's say we want to make an dictionary which converts English to French. So there will be keys in English having their values in French. So for this we can create a binary search tree. But the problem with this is like the common use words the will appear later in the tree, and maybe some other non-common words appear at the top. So to solve this problem, what we actually need is known as optimal binary tree, which will minimize our cost of search by giving the optimal tree structure according to the various frequencies with which the words occur. So let's see, like, this is our tree for converting English to French. Okay, these are the keys. This is maybe some English word we want to find its translation. So we are having this many words. So doesn't necessarily a word may not have any translation in French. So it can end up without stopping at this key. So it can be an unsuccessful search and can go to D0. That is all the values less than KI, which don't have any French translation, and greater than KI and less than K2, D1, D2, similarly D3. D5. So a search for a word can be either successful or non-successful. If it is successful, it will end up at one of the keys, and if non-successful, one of these D0, D1, we call them dummy keys. Okay, so DI refers to all the values between KI and KI plus 1. Okay, note this. Let's say we already know how common a word occurs and we know their probabilities. So another thing to note is that let Pi be the probability of key Ki, and the probability of getting a dummy key, that is a search which doesn't have a translation. So let Qi be the probability that the search will be for Di. Okay, so as the probability always equals to 1, we already know. So sigma of Pi I equal to 1 to n, sigma of I equal to 0, as there was D0 before K1, D0 to n, Qi equals to 1. This is the sum of probabilities, which equals to 1 for the whole search. Okay, so what our job is to minimize the expected cost. The cost in this context is the depth at which the key occurs plus 1. So if this is the depth 1, the cost will be the depth plus 1, that is 1 plus 1 equals to 2, as we search 2 times, first with the root and this, and the cost of this will be, this is the depth 2, so 2 plus 1 3, as we search through 1 2 3, so the cost is 3. So we can give the expression for this cost is such cost in it is sigma equal to 1 to n depth for ki, the search is for ki plus 1 and multiplied with its probability of occurring plus the same for the dummy keys, that is depth of di plus 1 and the probability of dummy keys qi. So multiplying pi with 1 and pi with this, qi with 1 and qi with this, so we will get this sigma of pi and sigma of qi plus the multiplication of these two. As we already know, this is 1, so sigma of I equals to 1, and let me just write it so that there should not be any confusion in this expression. qi plus this depth into a, sigma equals to 1 to n depth ki pi plus sigma I equal to 0 to n depth di qi. So this expression is equal to 1, that is the sum of probabilities. So our final expression becomes sigma equal to 1 to n, this whole thing. Okay, so this is our job in this problem, is to minimize this search cost, which equals to this expression. Okay, so before going on and moving to the steps of dynamic programming, I want you to note a few things. That we wrongly assume, as they seem sensible, but when we consider them in as a whole tree, it does not. What are these? First, an optimal binary search tree may not be the one with the smallest height. We wrongly assume it is, if this is small, this is the optimal, but it's not, as we are having various frequencies, so it matters as a whole. So when we consider frequency, we think that the optimal BST has greatest frequency as its root. This is also a wrong assumption. It can be good for the most probable word, like this we are having this here, but it will also affect the the structure of the subtrees. So this is also a wrong assumption. We always have to look at the whole tree. If we put the maximum like here, say the maximum occurring word is the, so this subtree will be having all the elements before t, which are actually a lot, and this one will be having a very few x, y, z kind of things which we rarely used. Okay, so moving on to solving the problem. So step 1, as always, is the structure of our optimal binary search tree. In optimizing a tree, we have to first optimize its subtrees. So let's take this subtree, let the subtree be with ki to kj, where I less than k less than j less than n. Okay, and since ki to kj, it will be having dummy keys, that is 1 less than di minus 1 to dj. So for a tree t to be optimal, it's having a subtree t dash having these keys and these dummy keys. This t dash should also be optimal. Okay, now we do. So this subtree will be having its own root kr, and so it divides into again two subtrees with keys ki to k r minus 1 and kr plus 1 to kj with dummy keys ti minus 1 to dr minus 1 and dr to dj. So in this way we will go on dividing and optimizing these subtrees. Okay. Another thing to note is about empty subtrees. Okay. If we are having just a di, let's see, if we are having this ki as a root, then there is no element on this side and everything will be on this side. Just there will be a dummy key di minus 1 on this side. So the expected cost for this case will be qi minus 1. So moving on to step 2. First, there is a easy case when j equal to I minus 1, as we were having ki to kj and j equal to I minus 1, means there are no actual keys, just a dummy key di minus 1. So the expected cost for this case will be just the probability of this, that is e for ei to j is I minus 1, so ei minus 1 will be qi minus 1. Okay. And when j is greater than equal to I, that is for our the subtree we took ki to kj, we have to select some root, that is kr. Okay, so the sum of probabilities for this, as a sum of probability for the whole tree, where it is so the sum of probability for the whole tree for all the keys and dummy keys was 1, which will not be the case for a subtree, and it will be having some actual sum. For a whole tree is it 1, but for this subtree, let's say the sum of probability is wi to wj. The probability of occurring between I to j is this, so it will be covering all L equal to 1 to j, all the probabilities of keys plus all the probabilities of dummy keys occurring in between. So this is the sum of probabilities for ki to kj. Now we choose kr as root, so we can get the expression, that is the estimated cost for I to j is the probability of the root pr plus, that is of I expected cost of the left subtree. See, we are having kr, then this, so the expected cost of this plus the probabilities of these subtrees from like this expression, probabilities of r minus 1 plus of this subtree, that is the estimated cost for r plus 1 to j plus the probability for r plus 1 to j. Okay, you can note a thing that for the sum of probability of this whole wij is nothing but this p of r plus w of I r minus 1. It can be written w of r plus 1 j. So the probability of left subtree, right subtree plus that of the root will be the probabilities of from I to j. So we can replace this in this equation. So our estimated cost expression becomes e of I r minus 1 plus e of r plus 1 j plus this w of I of j. So we finally got our expression. So we have to minimize this. Again, this recursive assumes that we know where we are going to divide, that is, we know which kr to choose the root, but we actually don't know, so we will try every value of r to be chosen as root and we will take the one having the minimum of it. So the final expression we will be getting is e of I of j is q of I minus 1, that is for the easy case for j equal to just having one di minus 1 dummy key. And the second we will be checking all the values, that is I less than r less than j of r, that is for root we will be trying every one of them, r minus 1 okay. The recursive solution will be having many overlapping and so it will be exponential in time, but in dynamic programming we will be saving the values while computing every one of them and then taking it back from the array, and finally what we will get will be the optimized cost for each of the subtree values from I to something whatever. So finally moving to our favorite step 3, that is actually computing the search cost. So computing now, so we are having these 3 tables to fill, that is expected cost from n plus 1. See, this is for the dummy key n plus 1, so till it goes to n plus 1. Then we are having another one having the sum of probabilities of everyone, and one more we will be using to store the root for, so if the value is for which is the optimal element to choose for I to j, this root of ij will be having that value. So starting our algorithm, for I equal to 1 to n plus 1, we have to first initialize them with the easy case in the start with just the probability of the dummy keys, that if this ki, before this ki there is just di where there is no, as it is the easy case was this. So we will initialize all of them with this and also the sum of probabilities. Now we will run our actual loop for L equal to 1 to n. This loop is the same as we did with the matrix multiplication. So for I equal to 1 to n minus L plus 1, j equal to I plus L minus 1, okay, E of I j. So initializing the expected cost, the one which we are calculating now, to be infinity, as we are minimizing, so anything minimum that will be take is a more optimal value to this. So our sum of probability will be I j equal to W, that is of the previous one, Pj plus Qj. Okay, now we don't know where to divide as root, so we will be checking all the values from I to j. This will be our cost, that is E of I r minus 1. As we have initialized this, so we will get our initial in the first iteration this. So this is the expression of the cost, r plus 1j plus the sum of probabilities of that subtree. Now if this cost becomes less for another iteration of r between in these, so we will be storing it in E of ij whenever we get an optimal solution for some r. E of ij will be having this cost, and the other one root, which is the best root between this I and j, is the r value we used for the best cost. So we return in the end both of these, expected cost and the root. So in this way we calculated the minimized our cost. See, we are minimizing it here, and we found the root. It will run as there are 3 for loops. Okay, for 3 for loops, so it will take the same time as that of matrix multiplication, and still it is the best time as compared to the recursive solution of this. So that's all in the optimal binary search tree. See you next time.